let's go. We now have the derivative. So now, let's apply it. The math gods bestowed upon us the knowledge, and they want us to use it. So, alright. What do we remember to be true about derivatives? So, let our minds float back to our calculus days. So, we prove a bunch of derivative rules, then we talk about why the hell do we even care? Well, one of the reasons we care is that derivatives allow us to detect minimums and maximums. So maximizing and or minimizing a function is not just important in mathematics, but any branch of study that uses math. Usually you're trying to minimize or maximize something, so derivatives telling us information about that is quite good. Now, of course, let your mind float back and remember that this is a P implies Q and not a P is equivalent to Q. If you have knowledge of min-max, that means the derivative is 0. So if you want to find them, set the derivative equal to 0 and see if those are minimum and maximum. So sort of it lets you figure out where they could be, and then you got to figure out, well, are they actually? All right, and as we know, you can be neither because of something like x cubed. All right, something else that is true about derivatives, the mean value theorem. So your average rate of change coincides with your instantaneous rate of change at some point. So if you travel 80 miles in 1 hour, at some point, you were going 80 miles an hour. Okay. Moving on. Derivatives. If your derivative is negative, you must be decreasing. Your slopes are pointing downwards, so your curve must be going down. If your derivative is 0, you must be constant. Your slopes are flat. And if you're increasing, your derivative is positive, right? Slopes are pointing up. Right, so again, we were not lied to in calculus. These are true. We will prove them, but again, we will be very precise about how we do it. And then finally, that thing from Calc 2 that you talked about for maybe like 10 minutes, and then you had to memorize and regurgitate on the final, Taylor's theorem. Specifically speaking, a function with enough derivatives can be reasonably approximated with a polynomial. In particular, a very nicely constructed polynomial. So something we didn't prove, and something we will not prove, is the Stone-Weierstrass theorem, which says that every continuous function can be approximated using polynomials. Taylor's theorem says that the ones that are differentiable, which, as we talked about last time, is not all of them, but some of them, the differentiable ones have a really nice polynomial. And we'll talk about that. Okay, and as per usual, we are going to make these statements as precise as we would like, not as possible. The super precise statement of Taylor's theorem is a junk, and I'm not going to do it. We'll get there. Alright, but we're going to make these as reasonable as possible, and we will prove them to be true, so let's do it. Alright, first things first, let's introduce the idea of a relative and minimum maximum, and the definition of these are not too shocking. Right? We'll say that you have a relative maximum at a point A if there's some delta so that anything within delta f of x is less than f of a. Likewise for relative minimum, and our usual min-maxes are relative. Right? So, like we said, Lebel refers to these as absolute min, absolute max, which is in line with what we do in calculus, but they're the maximum of the function and the minimum of the function. There's a reason to call them the absolute ones. Absolute I also kind of don't like, because it involves like absolute value maybe. Yeah. Relative, right, having min-max and then having relative ones, that's fine. It's a better use of language, I think. Anyway, but it's pretty easy to see, and here, continuing the tradition that's going to happen a lot here, where we're just going to go, we're going to prove one, then you figure out the other. Right. So it's super easy to see that if a function has a maximum, and indeed has a relative maximum at that point, we just need a delta. F of x is always less than f of a, so, alright, all the ones that are within 1 of it, whatever. Are there any? Yeah, a is within 1, so whatever, it's fine. Good stuff. Alright, cool. Alright, and as we remember, hopefully from calculus, the derivative can suss out, watch out, it can sussy out maximums and minimums, but it can only get the relative ones. If you want the absolutes, you gotta combine it with the extreme value theorem. But anyway, so let's state the theorem for that. Fermat's theorem is the name of that fact. If you have a function that's differentiable at C, And if it has a relative minimum or maximum at that point, the derivative must indeed be 0. Well, there you go. So, if you want to find relative mins and maxes, figure out when the derivative is 0 is a good step. Now, of course, it doesn't tell you for sure, but it tells you, well, if there are relative mins and maxes, they have to live where the derivative is 0. But as we noted, the derivative equaling 0 does not quite guarantee that. Okay. Worth noting here, for Frost theorem, like I mentioned, we're going to try to do most of our theorems with derivatives on non-degenerate intervals. For example, AB here is a non-degenerate interval, so we talk about it being differentiable. I'm going to say Fermat's theorem for closed-bounded intervals, AB. It works for any non-degenerate interval. The C, though, needs to be what's called an interior point, which I did not want to get into because that's just getting messy. And like I said, Lebel does everything on closed-bounded intervals, so I was like, all right, some of these will do on closed-bounded intervals, others will do on non-degenerate intervals. And Anyway, so Fermat's will do AB. Okay, now, before moving on, let's talk a little bit about Fermat. So Fermat's a name that you may or may not have ran into. So Fermat is a mathematician. He's actually sometimes referred to as the king of the amateurs, because Fermat was not a mathematician, even though I just said he was. No, so Fermat was actually a lawyer, and he just, did math for fun, like a normal person. Well, the thing is, Fermat is, of course, from the 1600s, and mathematician as a career wasn't really a thing. In general, mathematician as a career really wasn't a thing until the 1800s. And as a career now, it's, there are better choices you can make. But anyway, so Fermat you may have ran into in number theory, if you've taken that course, Math 350, because he's mostly did number theory. It's quite interesting. Like, this is like the only calculus thing I think that has his name attached to it. I think there's probably some other things that Fermat did that involve calculus, but he mostly worked with numbers and prime numbers specifically. But perhaps what he's most famous for, while this theorem is very nice, there is a much more impressive theorem with his name attached to it, and that's Fermat's last theorem. Note to be confused. My god, these slides. It's actually the second time I'm doing this video because there was a huge mistake and I had to completely scrap everything. And then I just noticed I said note to be confused. Side note, not to be confused with his last theorem, which is the assertion that for any integer bigger than 3, there do not exist natural numbers x, y, and z, so that x to the n plus y to the n is equal to z to the n. That is indeed Fermat's last theorem. Woo. So, this is quite an interesting theorem in mathematics because there's a lot of deep lore and intrigue here. So, note, why would you ever investigate this? Well, when n is equal to 2, this has solutions, right? 3, 4, 5, 5, 12, 13, right? The Pythagorean triples. So a natural thing is well, what if you cube them instead of squaring them? Does that work? And it turns out the answer is no. And in fact, it doesn't work if you do 4th powers. It does not work if you do 5th or 6th or 7th and beyond. So the origin of the claim is a notebook of Fermat's. And by a notebook, I don't particularly mean a notebook. It was a textbook he had. And in the margin, very famously, he wrote, "I have found a marvelous proof of the following, but I do not have the room for it." And it wasn't until, 300 years later that somebody actually proved it. Specifically Andrew Wiles, a British mathematician. For my French mathematician, so there you go. France loses again. Alright. They went on a lot of things, I guess. But anyway, so note the huge gap in the year between the actual statement and the actual proof. So let's talk a little bit about Fermat claiming things. So Fermat would claim stuff was true, and he would kind of just claim it to see what other people would do, because he would want to see what other people's proofs were. So sometimes he had a proof, other times he didn't. Other times he was like, I think this is true. And he would just say he proved it, and then see what other people cook up. This one is worth noting. He didn't actually formally announce this. This was in the notebook, and the only reason we know it was there was his son announced it. So after Fermat died, his son found it, and the alleged date is 1637. So, note, of course, the huge gap in the years, so most likely Fermat didn't actually prove it. And like I said, Fermat was a little trolly. He would claim things were true just to see if people could prove them. There was one thing he claimed that he definitely knew was false, and, and yeah, if you ever heard of things called Fermat primes, he knew that wasn't true, and he just said it was anyway. He claimed there were infinitely many of them, and as far as everyone's like, no, they're not. They stopped working at 5. So yeah. So if Fermat actually did know a proof of it, it's most likely wrong because Wiles, the proof of this, it's like 100 pages long, and it uses a bunch of stuff that Fermat would have never known about. So most likely Fermat didn't actually have it unless he had some absolutely ingenious idea that nobody has ever thought of before, but, good luck with that. Although it is worth noting, Fermat did actually prove it when n is equal to 4. And if I remember right, when n is prime, it's actually not too hard to prove this. There's some trick you can pull with n when n is prime. I forget exactly, but yeah, good stuff. So check this out. This is some good deep lore math if you haven't looked into it. All right, but let's prove his calculus theorem, which is a lot easier to prove. It didn't take 300 years and, let the curve nonsense. Yeah. All right, so let's actually do the proof of this. So, as per usual, we're only going to do the first one. Now, how do we even approach this? All right, well, let's think what we have. We've got a function that's differentiable, and we got a relative maximum. And I want to show something's equal to 0. Now, in analysis, when we want to prove something is equal to 0, we don't actually prove it's equal to 0. We show that it's always less than epsilon in absolute value. Well, given an epsilon, differentiability gives me a delta. I get another delta out of this, so I bet given an epsilon, I'm going to take a minimum of 2 deltas, and I'll show this is always less than or equal epsilon in absolute value, and then the proof's over. That's literally exactly what we're going to do. Let epsilon be greater than 0, there's a delta, so that the difference quotient behaves the way it should, makes the limit exists. As we got a relative max, we have another delta. I, of course, like to use eta for that, rather than delta 1 and delta 2. And then we're going to take the minimum of these two. We're going to call that nu. All right. Beautiful. Okay. So what do we do now? Well, if I have a point in AB that is within nu of C, not A. Oh my god. Yeah, like I said, I got it. This is the second time I'm doing this damn video, and there's still fucking mistakes. Serenity now on that one. It's supposed to be the Summer of George. No, it's not. Alright. Anyway, okay. So, we'll set nu equal to the minimum of delta and eta. Alright, so we will now find things that live in AB that are within nu of C, which means that they're within delta and they're within eta, so these two equations hold, and then we'll use that to the best of our ability. Okay, so, right. You can find an R that lives in the interval AB that satisfies this, and again, we can go through the whole specific process of creating this, but we've already done that multiple times. Hopefully we're fine with just, this exists. We know this exists. Let's not. Alright, so we can find an R that lives there. Now, note, since R now is guaranteed to be within nu of C strictly, we know it's less than eta, so that means we know that f of R must be less than or equal to f of C. Moreover, we are within delta and not equal to it, so we know that the derivative behaves accordingly. The difference quotient is within epsilon of f prime of C. Now, subtract this over. I know f of R minus f of C is less than 0. R was chosen less than C, so R minus C is less than 0. So this fraction right here, then, is positive. Right, negative times negative, so it's positive. So negative f prime of C is, right, less than or equal to it like that, because this is positive, added across the inequality. All right, we know it's strictly, it's greater than or equal to 0, so we know this must be true. And this is bounded above, of course, by the absolute value, which is less than epsilon. And so there we go. The derivative at C is strictly bigger than negative epsilon. All right. So, note what we did. We picked something to the left of C that we know had to exist. And there we go. And now we'll do the same thing. We can find a t that's on the right of c that's within nu. So that means, right, we know that f of t is less than or equal to c, and the derivative is and the difference quotient is behaving accordingly. Now, the only difference here is that this is positive and that is negative. So f prime of c is less than or equal to negative it. So note what I did there. This is, of course, less than or equal to the absolute value of this. And that's less than epsilon, so there we go. The derivative is less than epsilon in absolute value, so the derivative must equal 0. But boom, there we go. Proven. And as noted, for minimums, you can do the same proof. Okay. Where, right, this inequality flips, and yeah, it's not particularly interesting. Once you see the proof here, we're good. All right, no, not a bad proof. In fact, kind of a really neat little proof, right? It's just literally unraveling the definitions and applying everything. Great example of the kind of proofs that I really love, where every bit of the hypotheses was being used in a very sort of precise way. Everything is neatly set up so that all the theorems work. One brief comment that I want to make before we go any further is about the domain. So remember, differentiability is happening on non-degenerate intervals. And it turns out that you can replace the closed interval AB here with a non-degenerate interval, but you got to be very careful about C. Now note here, I'm ensuring C is not one of the endpoints. Now, not every interval has endpoints, but it turns out Fermat's theorem works for any non-degenerate interval as long as C is something called an interior point, which basically just means you can guarantee that are things that are to the left and things that are to the right. So the two things that we use there. So I could say this a little bit more generally, but we're only really going to use this for closed bounded intervals AB, so I didn't feel the need to go nuts with interior points already. Maybe I've gone a little too far in some places, but, you know, Fermat's a funnier character than we've ever had before. All right, so speaking of funny characters in math history, let's talk about Rolle. Rolle. All right, so sort of the same setup here for this theorem. Let's say I have a non-degenerate interval, AB. I have a function that is equal to 0 at the endpoints, a function that is continuous, and it's differentiable at every point not equal to A and B. So at the endpoints, maybe it's not differentiable, like a square root sort of thing, or, you know, the top half of a circle. Okay, then there must be a point in between A and B so that the derivative is equal to 0, right? And draw a picture of this. I have a continuous function. It's 0 at A and 0 at B, and we know it's differentiable, so it's not a weird jagged nightmare in between. All right, well, if you're 0, 0 and you're continuous, you got to start at 0, do something, and then get back to 0. Well, either you flatline, so your derivative is going to be 0, or you go up and then come back down, or you go down and come back up. You start at 0, you got to end at 0. Somewhere in between, you gotta turn down or turn up, so at some point you've got a derivative equal to 0. Alright, beautiful. Now, Rolle is quite an interesting theorem, an interesting character in math history. So Rolle proved this in 1691, and he proved it for polynomials specifically. And he actually did not use calculus at all to prove this. And in fact, Rolle thought calculus was a bunch of bullshit, essentially. Specifically, this is a Wikipedia quote. Who knows how true this is? Everything on the internet's true. Rolle said that calculus was inaccurate, based upon unsound reasoning, and was a collection of ingenious fallacies. Which, I mean, you know, if you're taking calculus, it's pretty true. Definitely the unsound reasoning part. That's definitely. I mean, he's not wrong. Now, you may, of course, be asking, well, if he thought calculus was bullshit, how was he taking derivatives? Note, for a polynomial, you can talk about its derivative without talking about calculus at all, because, right, given a polynomial, right, just power rule. Use the linearity of differentiation and the product rule, right? You give it a polynomial, you can take its derivative. And it's worth noting, too, time-wise as well, right, calculus was a thing, but people, when they talked about functions back then, they almost surely meant polynomials or pieces of polynomials glued together. Polynomials were kind of the main focus of mathematics for a very long time. Especially before, the Enlightenment began and everything. So if we're talking like 1500s, people were mostly focused on polynomials and solving them. So anyway, good stuff. All right, so we're going to prove this, and the good news is that we don't really need to do much to prove this because it is literally just going to follow from Fermat's theorem. Because, oh hey, what's my assumption? Continuous. Oh hey, closed-bounded interval. Oh hey, I have a minimum and a maximum. Oh hey, derivative's got to equal 0. So this theorem basically doesn't require any effort on our part. And in fact, because of that, even though Rolle historically, there's an interesting story here. There's actually some people that think that Rolle's theorem shouldn't ever be discussed because it's just so trivial from Fermat's theorem, as we're about to see. And also, as we're about to see, it's really just a special case of a much more powerful theorem, specifically the mean value theorem. So there's some people that act they're a little snobby about Rolle's theorem. But, I mean, when you prove the mean value theorem, you literally prove Rolle's theorem while you do it. So it's might as well just do it. And I don't know. Rolle's an interesting character. He actually did reverse his opinion, though, if you're interested. Eventually, he was like, oh, wait, calculus might actually be important. All right. But anyway, so basically, as I've already let loose, the proof of this is going to be super easy. The extreme value theorem gives us x and y, so we've got a minimum and maximum. Note that f of x needs to be less than or equal to f of y. And basically, there's two cases to consider. If these are equal, all right, well then, we're going to let alpha be equal to f of x. All right, for any t that lives between a and b, well, f of t needs to equal alpha, because f of t is stuck between the minimum and the maximum. All right, well then pick any point that's not a or b. For example, the midpoint. That gives me a point that lives between a and b, and its derivative is equal to 0. There we go. So if you're constant, nothing happens. You're flatlining, so the derivative is 0 everywhere, so just pick some point that's not equal to a or b. And here I went with the midpoint. Not a bad point. All right, now the worksheet case is what happens when the minimum and the maximum are not equal to each other. Okay. So it's got to be that one of them is not equal to 0. Right. Both of them can't be 0, and if one of them is 0, then the other one is not 0. Now, in the former case, that means that x has to actually not equal a or b, because by hypothesis, f of a and f of b are equal to 0. So note, we're using the hypotheses. We use the continuity. Now we're using this. So note over here we didn't actually need it, but again, if you're constant, then the derivative of 0, so there's nothing to say. All right, so x is in between there. Now, note, f has a relative max at c because it has a absolute minimum. Hey, it's x at c at x, and it's a minimum. What the shit am I? Oh my god! Swear to Yeezy. Swear on you, Tims, bro. Okay, there we go. My daughter Charlotte has been using the phrase "bro" a lot lately. I don't know where she got it. I'm sure she heard people say it, but she's been referring to things. She's been going like, "Yeah, bro." I don't know. Anyway. Okay, anyway, so yeah, since we've got a relative minimum at x, because we have the absolute minimum happening at x, Fermat's theorem guarantees the derivative of 0 at that point. And note, it's not equal to a or b. Right, and likewise, if f of y is the thing that's not equal to 0, then y, we have a relative max, and then Fermat's theorem jumps in and says the derivative is 0. Regardless, there's somewhere where the derivative is 0. Right, and there we go, Rolle's theorem proven. Beautiful. And like I said, there's some people that rag on Rolle's theorem and goes, there's no point talking about it because it's just the mean value theorem. But every proof of the mean value theorem that I know of uses Rolle's theorem, so might as well just prove it. And like I said, Rolle's kind of an interesting character. You should get some credit. All right, but let's prove the mean value theorem now. All right, so remember, the mean value theorem says that if you have a nice continuous function on a closed-bounded interval from a to b, and you're differentiable everywhere on the inside, then at some point the derivative is equal to the average rate of change. Beautiful. So the mean value theorem is actually quite interesting because you can easily convince yourself this is true by just drawing the picture. Draw a continuous function and, just draw the line attaching the points a, f a, and b, f b, right? Then, right, look at the slope of that. move it up, it's going to have to line up with the curve somewhere. So it's super easy to convince yourself that this is true, but an actual full-on proof of this was not figured out until like the late 1800s, which is quite shocking, but quite interesting. Anyway, and so like I said, the proof of the mean value theorem, at least the modern proof of this now, is the following. You set up this function, and then you note, oh hey, this function is equal to 0 at A and 0 at B. It's continuous and it's differentiable everywhere in between, so by Rolle's theorem, the derivative is equal to 0 somewhere, and hey, look at the derivative of this thing. This dies because it's constant, that dies because it's constant, and in fact the derivative here now is -1, so you just pick up negative this, and oh hey, this is exactly what I want to be true. I want that to equal 0, and we're done. So there you go. So this represents, which is quite shocking that this is like the proof of it now, because like I said, the proof of this took forever to figure out, and it's like so easy when you see it. It's like, why was everybody having a hard time with this? The reason everyone was having a hard time with formally proving the mean value theorem is that everyone was trying to attack it with epsilons and deltas, and actually it turns out that if you do that, it's super hard to prove. It's really weird. Like, so for example, Cauchy, our boy Cauchy, it came up with completely insane garbage that wasn't true, but it looked really convincing. But anyway, yeah. Okay, so here's the proof, and it's worth noting, the proof of this is pretty standard, and it's a technique that's used a lot with derivatives, is you want to show derivatives behave well, so you set up this other function, you take the derivative of that. This is a technique that shows up quite a bit to prove that facts about derivatives are true. Alright, well now we've proven the mean value theorem, quite easily, in fact. So now the question is, alright, what do we do? Alright, well we've ticked off 2 boxes. We've proven that derivatives give us min-maxes. We've now got the derivative gives us the mean value theorem. Instantaneous rate of change matches the average rate of change somewhere. Now what do you use the mean value theorem for? Well, the mean value theorem comes in and tells us some stuff about how derivatives behave on intervals. So let's say we have a non-degenerate interval, and we have a function that's differentiable at all points, n equal to 0. If your derivative is 0, then you've got to be a constant. Alright. So let's do it. Fix a point A in the interval, and let alpha be that f of A. I claim that that's going to be true for all x that live in A. Pick x and I. Obviously, if x is equal to A, then f of x is equal to alpha. So we can further assume that x is bigger than A, or it's less than A. And in the former, we'll prove things work, and note that in the latter, just flip an inequality, whatever. Alright, so what we're going to do is apply the mean value theorem, and now, like I said, the mean value theorem, it's just easier to state it for a closed-bounded interval and then apply it to non-degenerate intervals, as we are now doing right here. Alright, so we'll apply the mean value theorem to the mapping, that is the restriction of f to the set. Note, by hypothesis, it's continuous and differentiable everywhere. So the mean value theorem gives me a c, so that the derivative is equal to 0. Alright, but f of a is equal to alpha, and the only way this could possibly equal to 0 is if the top is 0, which means that f of x is equal to alpha. So derivative equaling 0 means that we're nice and constant. Hooray. Well, there we go. So if you're constant, your derivative is 0, and conversely, if your derivative is 0, you must be constant. Now, it's worth stressing here that this is, you need it to be true on every element in your non-degenerate interval. So it turns out, like I said, in order for our theorems to go well with derivatives, you need an interval to be what we're working with. Right? If you're thinking about the definition of differentiation, it seems like, oh, I could have just done it at a cluster point, right? You can, but yeah, this theorem is not true anymore. It turns out you can construct functions that are differentiable and the derivative is 0, but the function you actually have is a constant, and that's you can't have an interval, basically. Cool. So, like I said, though, our theorems for differentiability are mostly going to be on intervals, so we'll keep it that way. Alright, moving right along. So, something that we promised was that increasing plays a role with derivatives, so let's see how that happens. So, a function is said to be strictly increasing if, instead of our usual monotone increasing, instead of the inequality, we have strict inequality, right? And yeah, if you're strictly increasing your monotone, it's super easy, right? If x is less than or equal to 0, well, if they're equal, then things work. If they're strictly less than, by hypothesis, we're strict. So, boom, done. But of course, monotone increasing does not apply strictly, right? If you're monotone increasing, you could be flatlining, right? Because monotone allows for less than or equal to. But strict does not allow for that. All right, so as we learned from calculus, derivative positive means you're increasing, derivative negative means you're decreasing. And that's our goal, but before we get there, we got to prove another fact about intervals that's quite nice, involving cluster points. So, as we already know, if A is in our interval, then we know it must be a cluster point. It turns out, though, that it must be a cluster point of one of these sets here, if not both, meaning that I have access to left and right limits at those particular points, which we are going to exploit to our benefit here in a moment. All right, well, let's prove it. Okay, since we're non-degenerate, there's some B that's not equal to A. B's on the left or the right, so, hey, if it's on the right, then this is a cluster point. Hey, if it's on the left, it's a cluster point of this thing. And hey, once again, I'm just going to do half the work. You can do the other half. All right, let delta be greater than 0. Set A to be B minus A, our usual little trick. All right. Since A is less than B, A is strictly positive. Define nu to be the minimum of those two things. Note that it's got to be positive. Add it to A. I can find something between the two. That thing needs to be within delta of A, and it needs to live in my interval because it is between A and B both live in the interval, so anything between them is in my set. And there we go. So we got to be a cluster point on the right. Because we are to the right of A, we're within delta of A, and we live in our interval. There we go. Beautiful. Okay, so equipped with this, we are now finally in place to prove how derivatives and increasing work. So, specifically, for any non-degenerate interval and a differentiable function on that interval, monotone increasing and monotone decreasing is an if and only if. So if you're monotone increasing, your derivative has to be greater than or equal to 0. Likewise, if you're monotone increasing, your derivative is less than or equal to 0. However, it's not an if and only if for strict. If the derivative is positive, then you're strictly increasing. However, you actually can be strictly increasing but not have a strictly positive derivative. X cubed has to ruin the fun. Right? Strictly increasing function, and the derivative can hit 0. Boo. Boo earns to that one. But it is worth doing right. Well, strictly increasing derivative is greater than or equal to 0 everywhere, and then obviously you can just start throwing out where it's equal to 0. Okay. So, unfortunately, the converse of 3 and 4 is not true, but fortunately that means we don't need to do twice the work. All right. Okay, so we will prove 1, and I'll leave 2 to you. And then we'll prove 3, but then we're going to point out that the proof of 3 is basically the proof of 1. So this is there's 4 points here, but really we're only really going to be proving one thing. All right. Okay, so now we're going to see why we just did that cluster point thing, because if you're monotone increasing, pick a point that lives in I, then your cluster point for on the right or on the left, again, we'll consider the former. For any t then, the monotone increasing then guarantees that this is true, which means that the difference quotient coming in from the right is always positive. And by hypothesis, we know this limit exists, which means the limit coming in from the right exists. And since that's always greater than or equal to 0, that means the derivative must be greater than or equal equal to 0. And there we see sneaking that in. Good stuff. Cool, cool. Alright, so if you're monotone increasing, your derivative has got to be positive. And now note, you can see how you can't possibly extend this to strict. Because even if this is strict, that is strictly 0. That doesn't mean the limit is going to be strictly bigger. Now, if I knew there was some strictly positive constant in between the two, then I could guarantee it, but I wonder if that'd be like, oh, I don't know, homework problem or something. Yo. Alright, now conversely, suppose that the derivative is greater than greater than or equal to 0. We'll prove that we got to be monotone increasing, and pretty easy, pick A and B so if that's true. If they're equal, we don't have to do anything, so we assume they're strict. Mean value theorem then gives me a C so that I behave. We're monotone increasing. No, we're trying to prove monotone increasing. By assumption, this is greater than or equal to 0, and since B minus A is strictly positive, it's got to be that the top is greater than or equal to 0, and so AF of A is less than or equal to F of B. Point 2 is similar. Monotone decreasing if and only if derivative is less than or equal to 0. And now if your derivative is strictly positive, then you can get strict increasing by the exact same argument that we just made, only now this is strictly positive, and since that's strictly positive, this up here needs to be greater than or equal to 0, strictly greater than 0, so f of A is less than or equal to F of B, so we're strictly increasing. And there we go. Beauty. Alright. So, derivatives tell us min-maxes. Mean value theorem. Average rate of change is instantaneous rate of change. Derivatives tell me where I'm constant or increasing or decreasing. So the last thing to go after is good old Taylor's theorem. So, a little setup before we get there. Let's talk. So given a non-degenerate interval and a function is differentiable everywhere, you have access to the function whose derivative is defined accordingly. Okay. Now, no, like I said, you can technically talk about the derivative at any cluster point, but really, as we've already seen, we kind of want intervals for theorems here, so we're only going to consider differentiable functions on any interval. So if you're differentiable on an interval, you've got access to the following function. Now, since f prime is give any differentiable function, you can create f prime. Now, if f prime is differentiable itself, you can take the derivative of the derivative, and we call it the second derivative, and say that f is 2 times differentiable. Continuing in that fashion, we can then, of course, create the nth derivative, and say f as n times differentiable, and the notation we're going to use is this, which is a dumb, stupid notation, but we're going to use it. And it's used, it's fine. It's not the worst thing ever. Now, additionally, we will use the phrase continuously differentiable to mean that not only do the derivatives exist, but the derivative itself is a continuous function. Alright, well, if we have to give that a name, it's probably the case that you can be differentiable, but your derivative is not a continuous function. Side note, indeed, this is true. And the examples of these are almost always like awful functions. The classic example is this one right here. You can prove that the derivative is this thing, but f prime is not continuous at 0. This thing oscillates wildly around 0, so there's no hope of it being continuous. So when you say continuously differentiable, you need to, right? Because it's possible that your function has a derivative, but the derivative itself is not a continuous function. Right? Take the limit as x goes to 0. This does not equal 0. It's not continuous to 0 at all, in fact. Okay. So, if you're differentiable, the original function is continuous, but there's nothing saying your derivative is continuous. But there actually are some things you can say about a derivative. So it turns out that derivatives have the intermediate value property. So given a differentiable function, and any point that lives between f prime of A and f prime of B, f prime of C actually equals it. This is known as Darboux theorem. And we're not going to prove it. the proof of this is basically like the proof of the mean value theorem. You set up a function whose derivative is going to guarantee this holds, and then you're like, oh, well, we need that to equal 0, so you just kind of mean value theorem your way. So you just set some stuff up. There's some tricks, you gotta be a little careful, but it's not too bad. Okay, so given a differentiable function, its derivative has to have the intermediate value property, even though it's not continuous. So for example, this thing has the intermediate value property, but it's, this thing has the intermediate value property, but it does not have continuity. Alright, now, naturally, this then leads to the following question. Alright, well, if I have a differentiable function, is it possible that the derivative is not continuous anywhere? And the answer to that is no. If you have a function that's differentiable, its derivative has to be continuous somewhere. In fact, you can prove that its derivative has to be continuous almost everywhere, which is quite interesting. So if I have a differentiable function, its derivative is continuous at most places. So it's actually in line with what I said when we were talking about this before. A continuous function can't have a derivative. It's possible a continuous function fails to have a derivative everywhere. It turns out, though, that if you are the derivative of something, right, then continuity has to happen pretty much everywhere. So it's quite interesting. So it kind of lines up with the intuition that mathematicians did have, but they kind of had it reversed. If you're differentiable, then the derivative has to be continuous almost everywhere. They were thinking that if you're continuous, you have to be differentiable almost everywhere. It turns out what they were envisioning was actually this. So like I said, this proof isn't too bad. You just kind of set up a function and you do a proof. The proof of this, though, that's a challenge. If you want to have a bad time, go for this. Side note, the proof of this uses something called the Baire category theorem. So enjoy that if you're into it. All right, so let's now get to the last thing on our list, which is Taylor's theorem. Okay, so we need to do our little talk about continuously differentiable things, which will become apparent when we get the actual theorem. But for the time being, alright, so it's the Taylor polynomial of something. So given a non-degenerate interval I, and an element x naught, so we're going to use x naught as is tradition, and a n times differentiable function for any m less than or equal to n. You can define the mth order Taylor polynomial as follows. It's this polynomial. And here we're going to take the convention, right? Note, when m is equal to 0, no derivatives means it's just the original function. So this would be the 0th order, which is just constant. That would be the first order. There would be the second order. And that's all the way up to the nth order. Now remember, kind of the real power behind the Taylor polynomials and why you define them this way is that all of these derivatives line up with x naught, and then, oh yeah, look, my x naught's turned to a. They're like half a's and half x naughts. Oh my god, I swear, I'm losing it, man. My brain just don't work anymore. I don't know what to tell you. Yeah, sorry about that. Okay, so recall from calculus, hopefully, that kind of the power of these is that the derivatives of the polynomials line up with the values of the derivatives of the functions. Hence why the k factorial is down there. Right, clearly for 1 it works, and then when you take the derivative, that kills this, and that gives me this. Now note when I take the derivative, the 2 jumps to the front and kills this, so that these line up. Likewise, going all the way up to n, by the time we get here, you gotta take m derivatives to kill that. And now note, if you go 1 further, it kills the entire function. Beautiful. Alright, so those are the key features here of the Taylor polynomial, and equipped with that, we can now state, and we'll prove Taylor's theorem, or at least our version of Taylor's theorem, which is more in line with what you see in Calc 2. The textbook's proof of Taylor's theorem is a lot more precise and technical, and because of that, it's a lot more messy, and I didn't feel like doing that, so I'm just going to prove the version of Taylor's theorem that you see in calculus, which is the following. On a closed-bounded interval AB, pick any point x naught, okay? Then if you have an n plus 1 continuously differentiable function, then the nth order Taylor polynomial centered at x naught does a really good job of approximating your function, and it approximates it with an order of n plus 1 error. There's an m here, which we'll see in a moment what m is equal to. It turns out that there are many choices of m, and like I said, the more technical theorem, as we'll see, there's a very specific thing that m can be chosen to be. But anyway, that being said, let's prove it. Okay, so first things first, let's talk about that m. The n plus 1 derivative is continuous. We're on a closed-bounded interval, so that means it's bounded. So that means I can find a real number so that this happens. And if I wanted to have the best possible m, I would obviously pick the biggest thing my absolute value can take, which I know I can do because, again, it's continuous, so it's bounded. All right. So what some people will state with Taylor's theorem, to be more precise, is that you actually don't need the derivative to be continuous. You just need the derivative to be bounded. Whatever. Make it continuous. It's fine. All right. Now, let's pick a point x that lives in AB. If x is equal to x naught, then as we already noted, the Taylor polynomial is designed so that the derivatives of it coincide with our function at its center point. Well, no derivative. They must line up. Is equal to 0. Hooray. So we can further assume that x is bigger than 0 or x is less than 0. And as always, you get it. All right, so now what? All right, well, now we're going to do a little proofs. Okay, I used capital T, and now I hate it, because it looks like it's a function or something. Let's use tau. I went with T for Taylor, but tau would be better, because this is a constant. Okay. All right, so the way Taylor's theorem is going to work is basically how the proof of the mean value theorem is going to work. We're going to set up a function here, specifically this one right there. Maybe tau isn't the best. I'm going to put a c dot. I kept deciding. I kept going back and forth for what I should write here. Originally, I didn't have it as a constant. Note, Lebel does it, but he uses a capital M, which I've already used. So, but anyway, okay, that's better. All right. No, it's dumb. I don't like it. You know what I mean? Oh, you know what I'll do? This is what I'll do. This way. Okay. All right, here we go. Close brackets. Now you know. Gotcha. Okay. Anyway, so Taylor's theorem, which I'm about to see, is basically just the proof of the mean value theorem, but instead of doing it one time, you do it n times. So we set up a function, and note that we've set up a significantly more complicated thing here, and then we're going to start taking derivatives. Right, so again, note this has to be n plus 1 times differentiable, and its kth derivative would equal this, so you would take k derivatives of this, k derivatives of that, and tau, note, is a constant, right? X and x naught are fixed, t is our variable here, so tau goes for the ride. And then when we take derivatives of this, right, we're just going to start picking up an n plus 1, an n, a n minus 1, so on and so forth. Note, when I plug in x naught into this, these zero out. This is never equal to 0, so this zeroes out. And there we go. So we have constructed a function so that all of the kth derivatives at x naught are equal to 0, and that's going to give us kind of our pivot point to apply Rolle's theorem, because like I said, the proof of this is basically the proof of the mean value theorem, but you just do it instead of once, n times. So indeed, because g of x is also equal to 0, if you plug in x into this, now here I've replaced tau with what it is, these cancel, and then these knock that out. So since g of x and g of x0 is equal to 0, Rolle's theorem gives us an x1, so that the derivative is equal to 0. Since the derivative of x0 is guaranteed to be 0, you can apply Rolle's theorem again and get another point where it's equal to 0. And then you keep doing this until you get to the n plus 1 derivative. And there we go. So note, it's literally the mean value theorem right now. We set up a function, we hit some derivatives, used Rolle's theorem. And I'm getting attacked by Olive once more. All right. So now the proof's over. We got the derivative equal to 0. Note the n plus 1 derivative is this. Note the t minus x naught got killed because I took enough derivatives. It did give us an n plus 1 factorial, though. That's nice of it. All right, now this has to equal 0 at x naught at x sub n plus 1. All right, note the Taylor polynomial died as well because I took enough polynomial derivatives of it. All right, this is equal to 0. So that means that f of x minus p of x is equal to this. Pull this apart as follows. There's that quantity I was looking for. And here we see that there is a point where the n plus 1 derivative shows up. So Taylor's theorem, more precisely stated, is that this is equal to this very specific statement. But if it's nice and bounded, we get this is less than m, as we already noted, and thus concludes the proof, our proof of Taylor's theorem, and thus concludes our discussions of the applications of the derivative. And so now you might ask yourself, well, what's left? What do we do now? Well, there was a derivative rule that we didn't talk about. It's a rule that you learn. It's a very powerful rule. It tells you how to take certain derivatives that are very useful. And the theorems around it are quite shocking. So stay tuned for that.